Thank you. And thanks for inviting. So in the last talk, you saw that there's this notion of stable envelopes, and one of the main players were X, which was, well, let's say it's a symplectic resolution, which in my language will be the Higgs branch. Of a three-dimensional n=4 theory, but can also generalize, so can also do n=2. And then there was XA, the fixed locus, which is very natural to sort of realize again physically. But so in the last talk, it was fixed locus. For a certain torus A, acting on X, and it is sort of natural in the same spirit to think about it as, again, the Higgs branch of the same theory, but with certain masses turned on. The same QFT, but with generic real masses. Let me call it MR, or just M, because I will not have any other masses. So M, which are valued in some Lie algebra little a, where it's just the real Lie algebra underlying this torus that acts on X. So in physics, when you turn on masses, you sort of introduce potential on top of your modular space of vacuum, which is here, the Higgs branch. And it selects you some smaller subspace, which here is the fixed locus, because real masses, they are like, they're related to this action of torus on X, and you can think of them as this potential to be proportional to the magnitude of the vector field that generates the action, the torus action. And then the key idea is that there exists a natural supersymmetric interface, meaning that there's literally a wall in space on which the quantum field theory lives, such that on the left we have this QFT at 0 masses, and so the Higgs branch of this theory here is X. And I should have said here so that the Higgs branch, we assume here that the generic phi parameters, which means that this X is fully resolved, like at 0 Fi parameters, you have some symplectic singularity. Well, you usually, if the theory is superconformal. And then at generic Fi parameters, it is fully resolved. So on the left, we have this QFT at 0 masses whose Higgs branch is the full X. On the right, there's a QFT at large masses. So we take them to infinity within a certain chamber. Let me denote it like this. I'll say a bit more on this momentarily. So we take it to infinity in this the algebra A. And in this case here, the theory has as its Higgs branch the fixed locus. So that's one picture. Or alternatively, I could also consider things like where I have masses, non-zero masses on both sides, but they go to infinity within different chambers. So what are these chambers? Very briefly, if I draw the algebra A like this, just a vector space, just as a plane, there exists certain walls in this space such that when the masses take values at the wall, the size of the fixed locus jumps up. For generic values, you can imagine that there are only isolated fixed points. And then for certain non-generic values, they suddenly are not isolated and fail to be isolated. And there's some, say, a rational curve that connects the fixed points, which also featured in the previous talk. So this happens at certain walls, and this hyperplane arrangement sort of breaks your space into chambers, and then you can pick, let's say, chamber C1 and send your masses to infinity within this chamber. It turns out that the answer, whatever the answer will be, whatever I mean by the answer, depends only on the choice of chamber. Spoiler alert, this sort of natural supersymmetric, there exists a natural supersymmetric interface. It means that you sort of make these two quantum field theories talk to each other, interact in a supersymmetric way, and it actually realizes this stable envelope, elliptic stable envelope, associated to the choice of chamber C, which is the same thing as the co-character in the previous talk. As Michael said, that the dependence on co-character was only through the chamber in which it is valued. Now, to be more precise, so once you have such interface, you can ask various kind of, so to speak, BPS questions about this interface. We call the interface I. BPS questions, by which I mean that sort of study at the level of Q cohomology, or which is by Q, I mean the supercharge that is preserved by the interface, or look at the localization equations in the presence of this interface, stuff like that. For example, you could study BPS states or solitons where you have this interface, and let's say you choose vacuum 1 on the left, far away, vacuum 2 far away on the right, and you find that the associated equations, BPS equations, they have solutions which I schematically will depict like this, which are interpreted as, you can interpret them as particles living on the interface, which is like I said, something two-dimensional. You could ask, what is the vertex operator algebra supported by this interface? And these sort of questions, they actually kind of provide the categorification of a more basic construction, where you consider the supersymmetric index, or whatever people always call it Witten index, which counts such sort of particles living on the interface. In this case, I consider the theory, it's a three-dimensional theory on some elliptic curve. Let me denote it E tau, actually just E, cross R, which I think of as Euclidean time. Okay. So time direction. Then the picture is that the interface has the shape of a torus, so it's this elliptic curve, and the other direction is time. And let's say I pick vacuum 1 here, vacuum 2 here, and let's say that the time, this Euclidean time that I denote by y, runs in this direction. You could interpret this setup in various ways. You could also either say that it counts by making one of the circles to be actually the Euclidean time. You can say that this counts this sort of BPS solitons or whatever configurations. Or by treating y as time, you can say that this is interpreted interpret the sort of partition function of your quantum field theory on this configuration, which I will just draw like this, as matrix elements between the vacua, between the supersymmetric vacua of this interface. When I view it this way, I think of the interface as an actual operator, acting on the Hilbert space of a theory attached to this elliptic curve, or using the notations from Tudor's talk, I would still call this Z of E, because that's what your quantum field theory attaches to the surface, it's just the space of states. So, and then the idea is that this operator is actually, well, at least when you look at how it acts on the supersymmetric vacua, is what realizes the stable and elliptic stable envelope. Now let me go into slightly more details on this. So I want to tell you about two things, sort of the outline of the rest of the talk. Is first the statement or the slogan that elliptic, well, equivariant elliptic cohomology is basically the same, almost like the same thing as looking at supersymmetric vacua on the torus, so on this elliptic curve, when you think of it as a space. So in quantum field theory, we often declare this direction to be time. This is the spatial slice, and we study the Hilbert space associated to the spatial slice, and perhaps look for supersymmetric vacua. Now, description of this vacua is, in fact, can be understood in terms of elliptic cohomology. And then this second idea that I will explain is that this stable envelope is realized as an interface where the mass changes. Such interfaces are often called Janus interface. It refers, like, whenever you vary some kind of parameters of your theory in one of the space-time directions. Like, for example, here I vary mass as I go from the left to the right, and this is often called Janus interface. Or here for masses. And then tomorrow we'll explain about certain relation of this to vortex counting again. All right, so if we have, let me start with vacua, supersymmetric vacua. If we have a three-dimensional supersymmetric QFT, which lives on R3, so on non-compact space, then such theories often possess the moduli space of vacua, model space of vacua, which is in general some complicated variety, which has perhaps some different branches. Let me say that, let me call this X. There can be another branch that I will call X check. There can be some stuff in between, mixed. So this one is the Higgs branch. Coulomb branch. And there's some mixed branches. There is a physical way to distinguish which ones are Higgs and Coulomb, but you can just think of Higgs branch as something that you get by Hypercolor quotient, if a theory is a nice gauge theory. And Coulomb branch is something that you get by BFN type construction. That was featured earlier this week in some talks. And then here we think of a point, say point P in this space. P is actually related to sort of physical supersymmetry preserving vacuum. And when you are on R3, so when your theory is in non-compact space, you literally sit at the point of the modular space of vacuum, and you then can study fluctuations of your quantum fields around this vacuum. And by the way, I can also, at least within this setting, I can isolate the Higgs branch by turning on Fi parameters. Usually, well, at least in the class of theories, or equivalently by resolving it, because when the points where it intersects other branches are usually singularities. So if you're able to resolve X by turning Fi parameters, you effectively only are looking at the Higgs branch, and at least for some classes of questions, you can forget about the rest. Now, if I'm on, instead of R3, I am on R cross the elliptic curve, which is what I'm doing today. Then vacua are not really points on the Higgs branch anymore. Vacua are sort of wave functions that are somehow spread in a non-trivial way over the Higgs branch, and you can think of them as vacua in quantum mechanics of maps from R to maps from the elliptic curve to X. And I don't specify what kind of maps I'm looking at, because you might change the classes of maps you study along the way, depending on the physical question you're asking. But so this is a quantum, in general, for 3D n equals 4 theories, it's going to be n equals 8 quantum mechanics. Or if I start with 3D n equals 2, as I said, it can be generalized, then it's going to be n equals 4 quantum mechanics that featured in Andreas' talk. In his case, instead of an elliptic curve, you could have some homogeneous curve, and then in the presence of topological twist, you would have the number of supersymmetries. So even for n equals 4 theories, the quantum mechanics would be n equals 4. Okay, it's maybe the notation is a bit confusing. When I say quantum mechanics, then n equals something. This is literally the number of supercharges. Whereas in 3 dimensions, you should multiply this n by 2. So to get the actual number of supercharges. Anyways, in quantum mechanics, this vacua can be identified with a homology. In fact, it can be identified with equivariant cohomology of this space. So this space of maps from the elliptic curve to X, you can think of it as a double loop. And then you can study equivariant homology of this space, equivariant with respect to both loop rotations, because they're two one cycles of the torus, you can rotate them. Well, and this thing is roughly what you like. If you would try to make sense of this object in some way, you would end up building elliptic cohomology. Now, typically, X in this kind of problems is non-compact, and it sort of complicates, introduces various complications, and but often there's the torus T, which is the same T that was in the previous talk, where T is this A plus additional torus associated to character H bar that was the one scaling the symplectic structure. Yeah, these are maps from the torus to X. And so once you have such map, you can start rotating the one cycles of the torus. Yeah. Yeah. So with such T acting on X, XT is compact, often just a set of points. So it makes sense to include equivariant parameters, equivariance with respect to T as well. So I will include the equivariant parameters, which will denote little t. And they're realized physically as flat connections for T, so flat T connections on the elliptic curve. And then I can study equivariant cohomology, where in addition to this S1 cross S1, there's also T that acts on X. So then it naturally also acts on this space of maps. And you can think of elements of this space as equivariant elliptic cohomology classes of X. Now, this is not like the way I phrase it is not completely precise, but sometimes this is referred as the sigma model point of view on the elliptic cohomology, because you really study, basically you think of it as a sigma model in 3 dimensions from R cross E into X, and then you reformulate it as such quantum mechanical sigma model. Okay, the word sigma model refers to the quantum field theory of maps, basically, for here from R to anything in our case in this specific infinite dimensional target. Okay, so perhaps I should also say that, as I said before, as I said in words, this X branch is often just a Hypercolor quotient. So you start with some matter in complex representation R, and then you take Hypercolor quotient by the gauge group. And in this case, this C star H bar acts on the fibers. Well, I'll say in words, acts on the fibers of this T star R with, yeah, with charge 1. Now here I introduce this equivariant parameter T, which is flat connection for torus capital T. It also is convenient to split T into X and H bar, where X is the equivariant parameter for A, torus A, and this one is for torus C star H bar. In fact, already introducing H bar is enough to achieve compactness. Often, if you consider the fixed locus with respect to this C star H bar of X, for this sort of, well, say for quill varieties, you're gonna get the compact object, sometimes called compact core. So as I said, this T are equivariant, elliptic equivariant parameters. They are realized as flat connections for the torus T on the elliptic curve E. Let's say there are n of them. So they're really sort of coordinates on the nth power of the Jacobian of the curve. And this is what was called EET. In the previous talk, you also had EA, I think. And then ET also contains a factor for C star, for the H bar action. So anyhow, this is that abelian variety you had in the previous talk. Each TI, you can think of it as just a non-zero complex number with additional identification. Like this, so that it's valued in the elliptic curve, thought of multiplicatively. Now, these are flat connections for flavor symmetries. For what is usually referred as flavor symmetries. Which are the ones that act on the Higgs branch. In 3 dimensions, there are in addition symmetries that are in the physics literature called topological symmetries, which do not act on the Higgs branch, they act on the Coulomb branch, but nevertheless they are present in the theory. So, and you can also introduce flat connections for topological symmetries. So additionally, there are such parameters that are called little z. There's R of them. Again, they are coordinates in the rth power of the Jacobian, which now another abelian variety that I will call E script E with subscript A prime. In the literature on stable envelopes, on elliptic stable envelopes, they are called Keller parameters. And here A prime is just another torus. It's a torus of topological symmetries. In gauge theory. Roughly for each abelian factor, for each one factor in your gauge group, you get one factor of C star here. So let me already say that the elliptic equivariant cohomology of a point, as was mentioned in the previous talk, is precisely this, by definition, basically this abelian variety, the torus of flat T connections. Sometimes people also consider the extended equivariant elliptic cohomology, which is denoted just E, in which case one also throws in this variety of flat topological connections. So you can think of it as the general space of parameters that are compatible with a supersymmetric vacuum. Now, for every point A in this thing, so for every choice of flat connections for T and A prime, one can identify a subspace of supersymmetric ground states. in the Hilbert space on the elliptic curve. So this supersymmetric ground state, supersymmetric vacuum. And then you can consider sort of glue them all together. And okay, just write this to this. And they form a certain non-trivial bundle. I can call it the vacuum bundle. Over the space of flat connections. Now, for generic value of flat connections, the fiber, you decompose it. You can decompose it into sum of one-dimensional subspaces that are let's say there are a few of them that are associated to isolated massive vacua or gapped vacua. So here, this vector is just the one-dimensional vector space. Yeah, but, or massive, it's a synonym of vacuum. So it means that in the energy spectrum, there is a gap between the vacuum and the rest of states in the Hilbert space. And this vacuum remains gapless. It remains gapped. As I said, for A generic, which means that A belongs to this space minus a certain subset, let me call it D sub J, which has a certain positive, high enough codimension, but at this subspace, some of the isolated vacua, they become connected. So the picture you can envision is that there are, say, two isolated vacua, and at non-generic values, which correspond to this D, well, if this is vacuum, say, I and J, then there is a certain subset of, in the intersection of DI and DJ, such that for values A in this subset, the vacua become connected by a rational curve. So if you remove this subset, then the vacuum is gapped, and sort of this one-dimensional spaces, they can be again glued together. And they will give you a certain line bundle on this space, and it turns out that it can be extended to a line bundle just over the entire space of flat connections. But once you start looking at, so here I'm just focusing on the vacuum number J. But if you start looking at all of them together, the picture you get is that, so to each vacuum, I was sort of, I will depict by a line a copy of this ET of a point. Let's say this is for vacuum number 1. There's another copy of ET of a point for vacuum number 2, etc., etc. And there are these points which I show as the loci where they intersect, which correspond, let's say that this is I, vacuum number J, and this corresponds to this values of A that I denoted delta ij here. So this is where for such values of flat connections, the vacuum I and J, they start talking to each other. And the reason I show them as intersections because I'm actually going to identify these different copies of ET of a point at such loci. So what I'm going to do, I'm going to define the space ET of X as maybe I'll write it here. ET of X as a union of all this ET of a point. There are V of them, and then I quotient by equivalence where which says that ith and jth copies are glued along this delta ij, where the vacuums start talking to each other. Now, this is the extended elliptic homology variety of X. In fact, if in the way it is described here, the presence of topological symmetries doesn't affect any of this because, as I said, topological symmetries don't act on the Higgs branch. So ET of X can be written as something else called LT of X times this variety of flat topological connections. And this is the picture which is analogous to what you saw in the previous talk for the case of X given by P1, well, T star P1 really. Where it has two isolated points. There are corresponding two branches here that are identified at the origin where these two isolated vacuums start talking to each other. And okay, within 1 minute, let me say that these line bundles of vacua over each branch, they, in fact, they are equivalent if you restrict them to the intersections. They become equivalent there, which means that there is a single line bundle L over this entire space. They can be glued to a single line bundle. And then sections, if we have a section S, then we would say that this section S is what is sometimes called, they give you elliptic cohomology classes. One can, there are techniques in physics that go under the name of Berry connection that allow you to determine the topology of this bundle. So, so SUSY vacua are basically such sections or elliptic cohomology classes. And then one gets that if there is an interface of the sort I started with, so there's this interface wrapped on the elliptic curve such that on the left I have zero masses and on the right I have large masses. Then here on the left, vacua are associated with such, here vacua are sections of this L over ET of X. Whereas here, my Higgs branch is, let's say it's XA, which is just a collection of points, P1, PV. Right? So here, vacua are sections of some other bundle, which I'll call it LC because it depends on the choice of chamber where masses live. And now it's a bundle over the extended elliptic cohomology variety of this collection of points, which is just ET of a point. Disjoint union with a point V times, because now here the vacua are isolated in the presence of masses, so they never talk to each other. So such identifications never happen. So in the presence of masses, I just have a picture like this, just copies of ET and there are V of them. And so there's this disjoint union and a line bundle over each of them. And then the interface, which I don't have time to show, but there's some technical localization analysis which shows that the interface allows you to sort of, localizes you on these attractors that were shown in the previous talk that start from these isolated points. And this interface realizes the stable envelope as a map from the sections of this LC. Let me just write it for brevity like this, to the sections of L on the left, or in physics terms, it's just it just tells you how the vacua, supersymmetric vacua in the master and in the massless regime talk to each other. And I'll stop here and I will continue tomorrow with an application of this.
All right, let's thank Mykola.